Hello and welcome to this evening's lecture. If you've been watching these for a while and have not yet subscribed, I encourage you to subscribe. We plan to go on making more so that you can receive more information. If you're starting this for the first time, then maybe you want to go back and look at some of the earlier ones so that you have the background to understand the material in this evening's lecture. In any case, welcome. Today we're looking at capacitors, and first of all we ask ourselves the question, what is a capacitor? What is it? Well, a capacitor is just two conducting plates separated by a space. Obviously the plates have some surface area and we can put something inside of the space. Maybe it's just air or maybe it's some kind of an insulator, as shown there in the diagram. So that's all it really is. It's just the wires going into, those lines represent the wires going into two metal plates separated by some kind of insulating material. So the next question we are going to ask ourselves is, what affects one capacitor from the other? Clearly some will have a larger surface area. In some we will have a different dielectric, or the plates may be closer or farther apart. And these factors, its physical construction, affects how much electricity it can store. Capacitors behave like a battery, so think like a small rechargeable battery holding electricity. You can charge it up and you can discharge it. So then we have to ask ourselves, how does it work? How does it manage to store this wonderful charge that we're telling you about? Okay, well, it happens because the battery or electrical source that's connected to the capacitor is sort of forcing or pumping the electrons we've been talking about in previous lectures. So the battery actually forces electrons off of the top plate, as shown in the diagram, creating a shortage and making that plate positive, and it forces extra electrons onto the bottom plate, creating an excessive electrons on this plate. And what will help this process too is the natural attraction that positive and negative charges have. This creates what is called an electrostatic field between the two plates, whereas the positive ones on the top are attracted to the ones below, and the capacitor then becomes a storage or reservoir of electricity. Now what happens now if we try to take away the power source? Well, if we take it away, the charge is going to remain on the capacitor, and if we go and touch the two plates, we can get a big shock, literally speaking, if the voltage is high enough of the source. And people have actually been killed by this mechanism. So don't go around touching big capacitors with your bare fingers, because some of them can store this charge for years. Okay, so that's the nice story you can tell all your friends about this evening. Now we still are going to have a look now to see how we could possibly discharge this capacitor without causing destruction. If we put a resistor there instead of our fingers, the charge will gradually dissipate in a more slower fashion. The resistor slows down the flow of current and allows it to discharge over a longer period of time, and the energy that was contained in the capacitor gradually heats up the resistor. It may not get hot because if it's a small capacitor, there's not sufficient energy to make it get hot to your fingers, but that's the physics behind what actually happens. Okay, so now in an earlier lecture we compared water to electricity. Both of them flow, and in many respects the flow of water and the flow of electricity have some similarities. For example, we can collect water in a bucket, and we can collect electricity, loosely speaking, in a capacitor. But what are we actually collecting? What are we actually collecting? Well, it's charge. The basic electron has a very small charge, and when we have a whole big bunch of them, say millions of electrons, the accumulated charge from the number of them is what we're actually collecting. We're collecting charge, small particles of charge, and if we have a big load of them, then we've got a big charge. Okay, so just as you have different sizes of buckets, we are going to have different physical sizes of these capacitors, and their construction is going to create a certain metric by which we can rate a capacitor. Just like you have, say, a 5-gallon bucket that holds 5 gallons of water, we have a capacitor that will hold a certain amount, and we have another capacitor that will hold a different amount. Now we rate them by a thing called capacitance, which is the equivalent for capacitors to resistance is for resistors. So we say capacitors have capacitance and resistors have a certain resistance, and we're good to go. Okay? So the way that charge, voltage, and capacitance are related is a simple linear expression, and it's C equal to Q upon V, where C is the capacitance of our given capacitor, and Q is the charge it will hold for a certain voltage. Right. So that's a straightforward thing if the capacitor is fully charged. We've put on a certain voltage, a certain charge is accumulated, we simply divide that charge by the voltage, and that gives us a measure of how much capacitance that particular capacitor has. However, Ohm's law doesn't do that. Ohm's law relates voltage to current, and it would be convenient to have a formula that relates the capacitance to the voltage behavior and the current that's flowing through or into it. Put it that way, into it. The current that's flowing into it or out of it. Okay, so we want to have basically a voltage and current relationship with which to define the capacitance. That's what we're basically trying to achieve. But what is current? The current is really just a flow of charge, but rather it's the rate of change of the charge. Because if the charges are flowing and going somewhere else, there's going to be a certain rate of change of the charge. If we have a bunch of charges sitting there and some of them are flowing away, there's a rate of change as the charges get less and less. Now, you know, as you hear rate of change, we have a maths expression for that, and it's called differentiation. Now, if you haven't done differentiation in your mathematics, no great shakes, no big deal. But basically, just think of it as the rate of change. Rate of change, which is shown there on the right as dq over dt, and the t refers to time, rate of change of charge with respect to time. That gives us some value, which is the current. So, because it changes with time, we prefer to use lowercase letters for these instantaneous values at any point in time, and the large capital letters for, say, the total charge or the total current or the total voltage. So just bear that in mind. If you see a little I in a big I or a little V in a big V, the big V is the maximum voltage in the problem, and the small v is the voltage at the specific point in time that we are considering, because we've introduced the element of time into the behavior of these things. We have to have a way to understand what's going on. Okay, so let's take a closer look at this expression C equals Q upon V, so that we may determine at any point in time, while the capacitor is discharging or charging, the Q and V maintain their relationship to each other, but they're not changing in a linear fashion. This is the problem. The Q and V maintain a linear relationship with each other, but the two quantities, although they're changing together, they are changing in a non-linear manner. In fact, it's an exponential function, which is another mathematical terminology. But basically what it says is that the rate of change, or the amount it's changing, is dependent on the quantity. So if you've had that familiar experience with your iPad, huh? When your battery is fully charged, you have a lot of that stuff. And then as the battery goes down, the stuff gets less and the rate of change changes. So you don't get a linear discharge from 100% to, say, 10% on your cell phone. Okay, you don't. It just doesn't happen. So you can research that a little more. Anyway, the values at any point in time are given by this expression that we've just written down, where the Q, the small q and the small v are the instantaneous values. So we see that we have a rate of change on the Q and a rate of change on the V, and all we've done to get that lovely formula that you see there is bring the V over onto the C side. So we say Q is equal to CV, and then we differentiate the V and we differentiate the Q, because those quantities are actually rate of change. So we don't have to really do anything. They are differentials to start with, okay? And we as we said already, the I was a rate of change of charge with respect to time. So in the green formula there, we've merely replaced the dq over dt with the I, which we determined in the previous slide. So now if you look at our green formula, we actually have got what we want. We've got I equal to C dV upon T, which relates the capacitance, the voltage, and the current. Okay, now we have a complicated diagram here, and you don't, if you're not good at maths, you don't have to be stressed when you see these things and say, oh, there he's gone into serious algebra, or, you know, in fact, calculus. What you have to realize is what is actually being accomplished in what you see there before you. And once you look at that, you will understand it. We have a fully charged capacitor that is slowly discharging through our resistor R. So we've got a big V, which is the big voltage in the problem that's across the capacitor before we started. And as time progresses, the small VC across the capacitor is going to go smaller and smaller and smaller and smaller till it goes to nothing and the current ceases through the resistor. Okay, so we have a voltage that's gradually decaying to zero. You can understand that because the capacitor's electricity is being dissipated. The capacitor's charge is being dissipated as a current through the resistor. Now I wanted to show you expressly how we get there. Once we formulate the correct equations, all you require is the math knowledge to solve them. But this course is not about maths. This is about electronics. So if you can construct correct equations, you can go to your math buddy and get the solution, or use a calculator or something on the internet and get your solution. So we're starting here with KVL, Kirchhoff's voltage law around that circuit. And that gives us two voltages adding up to zero. So that's what we are doing. And you see the next thing we are doing here is we are using Ohm's law to replace the voltage with an IR statement. V equals IR. So we substitute I and R in place of V, but we know that I is equal to the dq upon dt, so we put that in place of the I. On the left-hand side of the expression, we are replacing the V with the Q upon C. Okay? So that's just coming from our formula C equals Q upon V. And all we've done is swap the C and V mathematically, algebraically, so that the V equals Q upon C. Okay, you see it right there before you. So what happens next? Well, we go to the solution. After you do all your bundle of mass, you come up with a couple of equations. Equation 1, 2, and 3. And we're just going to analyze the results to see what has actually happened. In this one, we have small I, and we have a term V upon R. The R is fixed. The V is also fixed because the big V was the initial voltage that was across the capacitor before it started to increase. And the exponential term, e raised to the power of minus t over RC, is the decay factor that reduces that quantity V upon R gradually to 0. So by plugging t in there, we can find the I at any point in time. Isn't that wonderful? You've got to love mass, huh? As a student of electronics, you need to become in love with mass. Okay? So we come down here now and we look at this next one in green, and we've done the same thing with the voltage. The big V was the initial voltage and the little v is the changing voltage. So the big V is always going to hold on to its big value which it started as, but the little v is going to start with the big V because it's going to start basically at 1, and that e to the minus t over RC term is going to start basically at 1 and gradually decay exponentially to 0. So that's how that is accounted for. Now, just to make sure you understand what it looks like, we've drawn a little graph for you to show you how the e to the minus t over RC decays over time. We have time on the horizontal axis and amplitude, and we see it coming down there in an exponential way. The curve tells you that it's exponential because a small amount of time you've had a big fall, but as it gets closer and closer to 0, it takes longer and longer time to fall. Okay, so that's when the capacitor was charged. But now what about when the capacitor is not charged? Here we're starting from an uncharged capacitor, and we're gradually charging it up through a resistor so that we can see its behavior. So we're working with the opposite scenario. The capacitor has 0 voltage across it when we first apply the power, and it's gradually going to charge up. And as the current decreases at the very end, all that big V will be across the capacitor, and there will be no current through the resistor at all. So that's an understanding in our head of what is happening, but we construct the equations in the same manner. Notice we've used the same KVL arrangement around the little circuit. And here now we have done, we've used Ohm's law and the expression for the capacitor again there to have the resistor behaving according to Ohm's law and the voltage associated with the capacitor behaving according to the capacitance formula. So you can study those carefully. And then the rest is just maths. Straight away down maths, and we come to the answers which we will analyze. Now I took the time and trouble to analyze this term for you because as you can see we have 1 minus e raised to minus t over RC. By it coming out in that mechanism, or that way it's come out, that term actually increases, okay? Increases over time. So that's why we have an exponential increase, whereas the other one is an exponential decrease, okay? Because initially we have 1 minus 1, which is 0, and then as the exponential term decreases, it rises to 1, okay? The overall term rises to 1. So basically we have little VC starting at 0 and eventually ending up at big V, which is the power of the power supply. And in this equation, we see that the current decreases with time in the same way it did. Big I there is the maximum current that flows. Little I is the current that equals big I at the beginning and gradually decays to zero. And we see that the charge also increases with time from 0 up to a maximum of Q, which is the most that capacitor can hold at that voltage. Well, that's been a heavy weight. I really should have, we've gone 20 minutes. I really should have put the inductors in a separate lecture. This is a long haul. So if you want to pause the video and go and get a snack from the fridge and come back, you can do that. But I have to continue. So here we have the inductor connected across a source. Now when we're talking about inductors, we're basically talking about coils of wire, which may or may not be wrapped around a metal bar, which is basically an electromagnet. You put on some power, you can use it to pick up stuff. As kids, we often play with these electromagnets, and they're used in a lot of nifty little gadgets. So we want to analyze what's really happening here. The electricity, the coil is converting the electricity into a magnetic field. It's an energy transfer mechanism. Okay, the magnetic field builds around the coil, and we can say that electricity is stored in the magnetic field. Okay, the magnetic field is just an energy transfer device, and the electricity has been stored in the magnetic field. After the field reaches its full strength, it's built up to the point where you can have no bigger field. There's no more need for any more energy in the magnetic field. It's at maximum. Therefore, what happens? Well, there's no voltage across the coil because it's just basically a piece of wire. Now it's just conducting. There's no change in the current flowing through it, and so there's no voltage across it, but the current is flowing as if it was a maximum because there's nothing to restrict the flow of current anymore. So it's behaving in all respects in an opposite way to the way the capacitor behaved, and that's a good thing. That's a good thing. The coils and the capacitors complement themselves in electronics to make a lot of nice things happen. Now let's have a look at the energy that was stored in the magnetic field. When we pull the coil away from the power, the energy it has to go somewhere. It can't simply disappear. So it's going to feed back. The magnetic field is going to collapse into the coil. It's just going to go back into the coil, and the coil is going to convert it back to electricity. Isn't that wonderful? That's why it's called Wonderful World of Electronics. And as we try to yank the power away, a big spark occurs. And if the voltage is high, we could get shocked or burnt if we're not doing it with our bare hands. But if it's a switch, the arc or spark may jump across the switch and actually fuse it, burn it out, or cause bad things to happen. Or we can actually destroy electric components in whatever this thing is used in, unless we take steps to avoid that happening. In the same way we use resistors to reduce the discharge current of capacitors, there are things that we can use to prevent damage and to slow down the removal of the energy out of the coil when we take the power off. So we designed the circuit that we can get rid of this energy in a safe way. Otherwise, we would have a lot of burnt out switches, electrical switches in various applications. Now, the property, let's examine the property. The property that physically defines an inductor, what separates one inductor from the next, is its inductance. And this inductance is a characteristic that depends on the physical design of the coil itself, how how many turns we have. Is it on a metal or an air coil? What is the diameter of the turns? Etc., etc. The physical characteristics. But this property of inductance is a measure really of the EMF force or voltage force that's generated by a given change in the current flowing through it. Because every time the current changes inside the coil, there's going to be a change in the magnetic field. And this change, either up or down, is either a bigger magnetic field or smaller magnetic field, is going to have a voltage effect, because the change is called self-inductance, because the change in the magnetic field, remember the coil is a transfer mechanism that converts magnetic energy into electrical energy, or vice versa, electrical energy into magnetic energy. And in fact, it's doing all two at the same time. So anytime you change the current, there's a change in the magnetic field. Anytime the magnetic field changes, the current's going to change as well, or the voltage basically, if you're changing the current. So the equation that relates the voltage, current, and inductance is as shown. Okay, it's the defining equation of the coil, which, as you compare that, you can go back and compare that with the capacitor, and you will see that basically the I and V have been swapped. Now, we are doing the same analysis we did before. We have a fully loaded coil. That coil has a big magnetic field around it, which is now about to collapse back into the coil to create the electricity. You notice there's no voltage source or anything inside this circuit. It's a fully charged coil which is about to discharge through the resistor as its magnetic field collapses. So once again, it's a very similar equation setup to the capacitor situation, and we're using the same KVL idea. I wanted to highlight the fact that we're using KVL, Ohm's law, plus the actual equation for the part itself to structure correct equations, which are then solved by mathematics. And if you haven't reached this mathematics yet, don't be discouraged by looking at it. You'll quickly understand it in due course, and then it will seem like, well, how did I ever have a problem with that? That's the worst thing that happens to students. They see something they don't understand, and instead of waiting or trying to analyze it, that gets them all discouraged, and they can't, get the resolution to continue. But we're continuing, and rapidly too, so you may have to rewind this, pause it, use it as necessary. Anyhow, our final answer is that we have the large current gradually decreasing over time to zero, with a formula now. The only change in this formula to the one that we had in the capacitor case is in the exponential function, where you can see it is minus RT over L. And the formula for the voltage is the same. So we're not going to labor anymore. Both the current and the voltage deteriorate exponentially, decrease exponentially to zero over time. But interestingly enough, I just want to bring to your attention again that the big I and the big V were the big initial voltage and the big current, the maximum current and maximum voltage that we will ever get in this problem as the whole thing deteriorates and the energy dissipates. Okay, last thing now and we're good to go. Let us look at the situation where we have a coil just sitting there and we're now about to put some energy into it and build its magnetic field. So basically you could say we have an uncharged coil and we're quickly now going to put some big power source on it through a resistor, of course, for safety's sake and also to make the calculations easier. We're going to, oh, by the way, this might be a good time to tell you that all coils basically have some resistance. So You know, I mean, if you connect the coil without a resistor, bad things are only going to happen if the wire gauge is too high or there are too few turns on the coil. But I digress. Let's get back to basics. We're starting with the KVL equation again, and it looks very familiar by now. We've got the equation there for the particular inductance, and we've got an Ohm's law there on the resistor R. So the setup is pretty much the same. We do some fancy math, which is going to be easy for you in a few years or months, depending on how fast you progress. And down here at the bottom, we have a very similar situation to what we had in the other one. The voltage across the coil decreases with time until the coil is just behaving like a piece of wire, or very little voltage is dropped across it because of its residual resistance, and the maximum voltage is dropped across R. R shown there at the top. Now we're just focusing here now on the current increase. The current increases up to the maximum that you can have for that circuit. Initially, we don't have a current, but the current builds and builds and builds, and then the only thing that limits the current at the end, when our magnetic field is totally built, is the R of the resistor there, and of course whatever voltage we have. We haven't specified a voltage on the voltage source, but clearly wherever big V appears in the problem, big V is the fixed constant applied voltage by that voltage source there. Alright guys, well, thanks for watching the channel, and thanks for watching this video. It's been exceedingly long. I don't know how many of you made it to the end. You don't have to make it to the end in one go, but I'm going to try and keep the other ones shorter and split them up. Didn't realize this would take so long. See you in the next video, and thanks for tuning in.